tonight, we're going to talk about Chapter 11. Chapter 11 is about measurement and data quality. So measurement is the assignment of, and should I say measurement in quantitative research, is the assignment of numbers that represent a specific amount of whatever variable it is that you're looking at, that a object or a person has. And you do this using very specific rules. The advantage is that there's not much guesswork. It provides very precise information, and it's not as vague to assess than words. There's 4 different types of measurement, 4 different levels of measurement. There's nominal, where you're assigning numbers to classify characteristics into categories. So there's no rank to a nominal level of measurement. In other words, this would be something like color: red, blue, green, black. And red would get a 1, blue would get a 2, and green would get a 3, and black would get a 4. But let's say we're evaluating somebody's favorite color. But there's no ranking to the 1, 2, 3, or 4. 4 is not better than 1, 2, etc. And another good example of that is gender. You maybe give males a 1 and females a 2, or the opposite, females a 1 and males a 2. But again, there's no difference in those numbers outside of it's just a symbol for that category. In ordinal, there is now some rank meaning to those variables. So for example, I might ask you, what is your satisfaction with the book on a scale of 1 to 5? And 1, might think it sucks. 5 means you think it's great. So there is meaning in the differences between 1, 2, 3, 4, and 5 now. What interval adds is intervals giving you the amount and the distance between the 1, 2, 3, 4, or 5. In other words, let's go back to ordinal for a second. The difference between I can't stand the text and I think the text is just okay might not be the same as I kind of like the text and I love the text. Those differences don't necessarily equate, and they don't equate the same for everybody. In an interval level scale, for instance, let's say Fahrenheit temperature, the difference between 71 degrees and 72 degrees is the same as the difference between 72 degrees and 73 degrees. Did I say that right? So 71 and 72 is the same as 72 and 73. The difference between the numbers, not only are they ranked as they are in ordinal, but now the distance is the same. The only difference between interval and ratio scale is that a ratio scale has a meaningful 0. So in other words, you can have none of that variable. So for instance, length. You can have something that has 0 length. It doesn't really exist, but you can go down to 0. With Fahrenheit temperature, 0 doesn't mean null, as it would have to be in order to be ratio. And that's why Fahrenheit temperature is an interval level scale. A 0 on the Fahrenheit scale still means something. It doesn't mean lack of something. So a variable's level of measurement determines what type of statistical analysis we're able to do on it. One of the things that's really important is errors of measurement. An error of measurement contains 2 pieces. It is the person's true score plus or minus error. Now, the obtained score equals true score plus or minus error. The obtained score is the data value that we get from the participant. So example, if we give them an anxiety scale, it is the score that they give us. But that doesn't necessarily mean it's their true score. Maybe we asked it in such a way that to them was vague, and we're not getting their true level of anxiety. We never know the true level of anything. It's always an estimate, and so there's always error. And error can be caused by many different factors. There can be situational contaminants. Maybe when we're asking them about their anxiety, something happened that made them more anxious. So maybe we're getting a higher level of anxiety than that we might have gotten had it been a less stressful situation. Maybe they're really, really tired, and so they are not thinking about how anxious they are typically, and they just want to get it done with. There's response biases. So in other words, maybe you have a 1 to 7 scale, and the 1 and the 7 are extreme versions of something, and there are some people that will just never respond on an extreme answer, and then there's some people that always respond on an extreme answer. Or maybe we don't have enough of the of the, for example, anxiety items sampled that we're really getting their true anxiety score. So that's what item sampling means. We haven't measured that with enough items to get a good representation of that person's anxiety level. So one of the things that becomes really important because there is error is reliability. We want to know how reliable a measurement is. And reliability is all about accuracy and consistency. We want to know how well that measure is reliably measuring what we think we're measuring. So a reliability assessment involves computing a reliability coefficient. Coefficients can range anywhere from 0 to 1, and typically those below 70 are considered unsatisfactory, and coefficients of 80 or higher are considered good. There's three types of reliability. There's stability, internal consistency, and equivalence. We'll talk about each one. So stability means the extent to which scores are similar on two separate administrations. So let's say, let's go back to our anxiety example for a second, and we give them the anxiety test one day and we give it to them a week later. It's how much do those two correlate? How close are they? How much are they coming up with the same level of anxiety? Now, sometimes anxiety isn't something that's necessarily very stable. So you tend to want to do this on traits that are relatively stable or enduring characteristics. For example, creativity. People aren't usually creative one day and not creative the next. Internal consistency is talking about the extent to which all the items on an instrument are measuring the same attribute. So you are evaluating an instrument on just one occasion, so we're not doing it on two occasions like you are doing in test-retest reliability, and you're doing it one time. And this is something that you do for most multi-item instruments, and it's the most widely used approach to assessing reliability. So let's now talk about a pain scale. So let's say we think we have a pain scale, and what we want to make sure is that all of the items on our pain scale are really measuring pain. They're really measuring the same thing. Maybe we have an item that's really measuring how they feel, and it's more a measure of like a depression than pain. So if we did our coefficient alpha, it would probably be a little bit low because we have items in there that aren't measuring pain, but they're measuring depression. So it's how internally consistent, how much do these items measure the same thing? Equivalence is the degree of similarity between different forms of an instrument or between different raters using the same instrument. So let's say I'll give probably the best example of different instruments measuring the same thing, so alternate forms, is let's say there are two versions of a test. And it's a test of a skill that you needed to acquire in one of your nursing labs. And maybe there's two different sets of it because they want to be able to measure you on multiple different time points, but they don't want to have what's called a practice effect, where once you do it, you kind of know it. They really want to know, are you obtaining that skill? So they might have two different versions of that test, but they believe they're measuring the same thing. So how similar those tests are would mean how reliable those tests are. Another example is when you're doing some kind of a structured observation and you have two people watching the same thing. Do those two people agree? So is their rating reliable? Their inner rater reliability, is that really good? So some of the important reliability principles to think about is that if you have low reliability, it can really undermine your ability to adequately test your hypothesis. You might not be able to find an effect that's really there because you're using an unreliable measure. Reliability estimates vary depending on how you obtain them. For example, if you're doing test-retest reliability and you are doing them a week apart, you might get much better and much higher reliability coefficient than if you measure them 6 months apart. It might be very low then. Reliability is lower if you have a pain scale and it has 10 items. It's going to be more reliable than a pain scale that maybe only has 2 items, because you're measuring more of that construct. The probability that you're going to get a better assessment of that construct is better the more number of items you have on a scale. Validity in measurement is the degree to which that instrument measures what it's supposed to measure. And there's four common aspects of validity. There's face validity, content validity, criterion-related validity, and construct validity. Face validity refers to whether an instrument just looks like it's measuring what it's supposed to measure. So, for example, if you're looking at what you think is a depression scale, and there are all sorts of questions about fear, then you probably don't have a depression scale. Content validity is the degree to which an instrument has an adequate sample of the items. So, for instance, if I have a depression scale and I'm only talking about sadness and crying, I probably don't have very good content validity because I haven't measured enough of that construct. And there, although unlike face validity, where there isn't a number that you can come up with for face validity, there is an index that you can identify for content validity. It's called the Content Validity Index. Criterion-related validity is the degree to which an instrument is related to some kind of an external criterion. So the validity coefficient is the correlation between the scores on the instrument that you're assessing and a criterion. A criterion could be like a gold standard. So there's two different types. One of them is predictive validity, and the other is concurrent. In predictive validity, I'm interested in the instrument's ability to distinguish people whose performance on this measurement, how that difference is predicting how they'll do on something in the future. For example, think about GREs and ACTs and SATs. Those are trying to take someone's score on that measurement and predict how well they'll do in the future. So a SAT scores and how well it correlates with college GPA would be an example of predictive validity. Concurrent validity is how well an instrument is correlating with something that's happening in the present time. So, for example, let's just pretend that we had some kind of a biological